All right, today we're going to look at pressure. Now, pressure is going to be the ratio of force to area. Ratio of force to area. And so, equation-wise, we have pressure, which is a capital P, is equal to force divided by the area. So we have capital P, which is pressure. We have the force, which is measured in newtons. And this is the force that is exerted by the fluid perpendicular to the surface. So oftentimes you will see a little perpendicular there. So force exerted by fluid perpendicular to the surface. And then we had A. A is the surface area, which would be in meters squared. So looking at our equation for pressure, well, we know it's going to be a Newton over a meter squared. Or we can say this is 1 Pascal, which is capital P, lowercase a, where 1 Pascal is equal to 1 Newton per meter squared. What causes pressure? Well, there's two different things that cause pressure. The first is due to thermal motion of molecules. So what that means is that when you have molecules, they're going to be slowly moving around inside of your container. And as they're moving around, some of them are going to hit the top and bottom and the sides. And when that happens, the particles are going to collide with those walls, and it's going to create a force in that collision. That force is the pressure. So particles collide with the walls of the container. And then the collision create a force. This is pressure at the microscopic level. So this is looking what's happening with the particles for each individual one. The second thing you can do to think about pressure is to think about it due to gravity. Now what this means is that if you are in some fluid, that above you are these layers and layers and layers of fluid. And each one of those layers is going to be applying some force down. So the weight of the fluid above you is what is creating that pressure, what's creating that force. So the weight of the fluid, this means that the deeper you go, the more the fluid is stacked above you, the more weight that is pressing down on you. So the deeper you go, the more fluid is stacked above you. And presses down. This is used to show that you have these different pressures at different depths or altitudes. So you have different pressures at different depths. At different depths. This is really looking at the microscopic level. You can also think of this as like changing the temperature is also going to create those more collisions. So that would also change your pressure here. All right. The next thing is the two different types of pressure. We have atmospheric pressure. We have absolute pressure, and we have gauge pressure. When we're talking about absolute pressure, this is the true pressure or the total pressure. We do ABS for absolute. The absolute pressure is equal to the gauge pressure plus the atmospheric pressure. So ATM stands for atmospheric. And that is saying this is the pressure of our atmosphere at sea level. So this is going to be the pressure at sea level. 1 atmosphere of pressure is 1 times 10 to the 5th pascals. This is something that is useful to know. And I don't believe that equation is given on your formula sheet. All right. Now, if we're talking about gauge pressure is going to be the relative pressure that's either above or below what the atmospheric pressure is. So when we air up a bike tire, you look at the gauge pressure. You're looking at the differences between the pressure inside that tire and the pressure of the environment. So we're looking at the gauge pressure. To do the gauge pressure, wow, I cannot spell. Gauge, G-A-U-G-E. The gauge pressure is going to be the absolute pressure minus the atmospheric pressure. So again, the absolute is the true pressure at that location. And if you remove what the atmosphere is, it's telling you what is the pressure that you physically see the difference of. That's what we're looking at there. It's relative to the atmospheric pressure. I did it up here too. AU. Great. All right, so we have an example here. A vertical column made of cement has a base area of 0.5 meters squared. So we have a vertical column here. And I know that the area of the base is going to be 0.5 meters squared. We know that the height of this is 2 meters. And we know that the density, that's rho, the density is 3,000 kilogram per meter squared, or meter cubed. All right, the question is, how much pressure does the column exert on the ground? So we want to know, what is the pressure here? Well, I know that pressure is the force divided by the area. Now, if we're thinking about what force this column can exert, well, the force is going to be the force of gravity. So I can replace this with the force of gravity, which is mg. Now, mass, we actually learned something about mass the other day, where we said that the density of an object is the mass divided by its volume. So if I rearrange that and I solve for mass, the mass is going to be the density of the object times the volume. So let's just replace this in our equation. So we're going to replace M with the density times the volume. So we have rho volume times G divided by the area. Next thing we want to do is look at the volume. The volume for any sort of prism is going to be the area of the base times the height. And so if we rewrite just our V here, we know that the volume, capital V, volume, is going to be the area of the base times the height. So now we have rho times A times H times G divided by A. Now the next thing is my area is going to cancel out. So really I have that the pressure at this location is rho times H times G. Now all I have to do is plug this in. My density I know is 3,000. The height is the height of my cement block, which is 2. And then last is the acceleration due to gravity, which is 10. When you plug this in, we have 60,000. And then the units for pressure are pascals, PA. So that means it is doing 60,000 newtons per meter cubed. Or sorry, newtons per meter squared. It's doing 60,000 pascals. Next up, we're looking at the hydrostatic pressure. This is with statics. So if you have an object and you take that object and you push it underwater, think about taking like a pool noodle, and if you barely hold it under the water, comparing to if you try to push it all the way down to the bottom of the pool, or maybe even like a basketball or something like that. If you try to push that to the bottom of the pool, it's really difficult. So the question is, why is there more pressure at the bottom of the pool? Well, there's several ways you can think of this. I think the easiest way is to just think about how much water is on top of it. Again, we have these layers. And so if you think about each layer, you have a ton more layers the further down it goes. And so the reason is due to gravity. Every layer is going to push down on the layer below it. All right, the last is going to be to relate the pressure to the surface, the pressure at the surface to kind of everywhere else. And so I actually want to take us to just a little side note here. This is essentially what we have going on. We have some object where we are looking at some point. What is the difference of pressure when it's underwater compared to at the top? Well, at the top, we have the pressure at the surface. And so the pressure at the surface is going to be applying this downwards force on our object. We also have the weight of this. The downwards force is going to be due to the pressure. Well, we know pressure is equal to force divided by the area. Therefore, force is really just the pressure times the area. And so the pressure is going to be the atmospheric pressure, or the pressure at the surface, which we'll say is P naught, times the surface area. Now our little object has some weight to it, so we have the force of gravity, which is equal to mg, pulling that down. And then we have one more force here, and that is the force from the bottom. Because as this water is moving around here, the water is actually applying a force in all directions. And when it does that, the surface is going to push directly back up. So we actually also have pressure from the bottom here, trying to pull this guy back up. So this is pressure pushing up from the depths. Okay. If you were to draw a free body diagram on this particle here, we have the weight of our object, and we have the force at the surface times the area. On the other end, we have the pressure from the bottom of the table. And so we have this one force that's going up, and that is the pressure times, that's going to be the true pressure here, times the area. If this object is at rest, it's floating at this location, what that tells us is that the net force is equal to 0. If the net force is equal to 0, we can actually plug in a couple of different things here. Because I know that the net force is going to say that all the upwards forces have to balance with the downwards forces. And so because of that, I'm going to set the forces that are going upwards, which is P times A, equal to the forces going downwards, which is mg plus P naught A. Now, what I want to do is I want to solve as much as I can for the gauge pressure. I know that the gauge pressure is going to take the atmospheric pressure and remove that amount from the true absolute pressure. And so if I get my pressures together, I'm going to actually subtract the atmospheric pressure on both sides to look like this. Now you might notice that the area is in common between these two pressures. So we have area times the difference of our pressures. So again, absolute pressure minus the atmospheric pressure is equal to m times g. So this is the atmospheric, this is the total. All right, we can continue going here because if we're dealing with fluids, we're actually going to change how we think of our mass, or how we think of our mass. We know the density is equal to mass divided by volume. And so if I wanted to rearrange this, I can say that the mass is going to be the density times the volume. So let's replace that in there. So I have A times P minus P naught is equal to rho V times G. Let's clean this up a little bit more. We know that the difference of our pressures is really just the atmospheric pressure. Sorry, the gauge pressure. The next thing that we're going to look at is the velocity or the volume, because I know that volume is equal to the shape of the base, which is the area, times the height. So if I replace this, I have the density times the area of the base times the height times G. Now the nice thing about what we have here is that we have A in both terms. So I can divide by A and cancel that. And what that tells me is that the gauge pressure is equal to the density times the height times gravity. So going back to our notes here, we have a couple of different equations we're going to use. The first one is how to find the true pressure, or like the absolute pressure. And what that tells us is that the pressure, again, or the absolute pressure, is equal to the initial pressure at the surface of the liquid plus rho GH. This is what we just derived. The only thing different is we don't have the gauge part. So that's our first equation. The second equation is that if I just want to do this as P minus P naught, then that's going to get me the gauge. And the gauge pressure is just rho GH. That's it. We know that when a fluid is at rest in a container, that all portions of the fluid must be in static equilibrium, and all points of the same depth must have the same pressure. This is implied in any physics problem, any ones that you see where you're like, man, that bike just isn't working quite right. We know that these two things are true for it, and this is always going to be the case. All right, last thing here. This is just showing you those forces again. So this is exactly what we derived a second ago. I just want you to see that there are forces that are going this direction, but notice those forces are also balanced. So we're focusing on the y direction because that's going to give us a lot of information.